So this is where we were when we left off yesterday, where we were talking about how deep learning has evolved, and there are these four axes that we were considering, and we have already talked in detail about the first two, and today we'll start a discussion on better activation functions, right? So that's where we are. So with that, let me just go to the next module. Yeah. So before we look at these activation functions, right? So let's try to first motivate why do we need to talk about activation functions, and the motivation comes if we try to introspect this question: what makes deep neural nets powerful, right? And we already saw this briefly when we were talking about the universal, not briefly actually, quite in detail when we were talking about the universal approximation theorem. So I just want to revisit that, right, and emphasize on some a component of the deep neural network which is important in granting it its power, right? So let's see what that is. So now suppose I have this deep neural network, right? It's a thin network, but doesn't matter, it's still a deep neural network. And suppose all my sigmas, which are the sigmoid or the logistic function, I just replace them by a simple linear transformation, right? So earlier I had a, any of the a's is equal to w into h plus b, and then h was sigmoid of a. So I'm just saying instead of h equal to sigmoid of a, if I just make it h equal to a, right? So there's only a linear layer and there is no non-linear layer. So that's the situation that I'm considering. So this is what it would look like, right? So y is a function of x. So x first gets transformed linearly by w1. So that is what a1 is. a1 is w1 into x. But then h1 is just a1, so it is again w1 into x, and this x is the input to the next layer, and then you get w2 is into w1 into x, right? So w2 into h1, which is w2 into w1 into x, which is the same as h2, right? Because h2 is equal to a2, and so on. You continue, and your output is just a linear, it's just a multiplication of weights by the input x, right? And now here, this is as good as just having a single linear transformation, right? So this is just as good as saying that y is equal to some wx, where w is a product of these four w's, right? So this is just a linear transformation. This is not, even though it's a deep network, it does not add any value to me beyond what a linear transformation would add, right? So the depth of the network is not what solely gives the deep neural network a power. Of course, it plays a role because then you have these composite non-linearities. But if you remove the non-linearities, then you just have a linear transformation of x, and then you are just going to learn linear decision boundaries, right? Because you have just said that y is equal to wx. So your y, you are just assuming that the relationship between y and x is given by a line or a hyperplane in higher dimensions, right? So then in particular, if you have these complex decision boundaries like that we had here, where you really need something non-linear, right? So here you're not learning a line, you need something like a circular decision boundary which separates the positive points which are inside the brown points from the negative points which are the blue points, right? I cannot draw any line which suitably separates my the brown points from the blue points, right, without giving me a high error. So that is not possible, right? So the reason a deep neural network can learn such arbitrary boundaries and hence act as a universal approximator, right? Because now we have a very complex function between y and x, which is looking like this, right? This is the function that we are interested in. And as we had seen while looking at the universal approximation theorem and the illustrative proof of it, where we had drawn these towers, we could do that because we had a non-linear layer, right? What the theorem said is that if you have even a single sigmoid layer, then you can, then the network can act as a universal approximator. So sigmoid was important there, right? So these non-linearities are what give deep neural networks their power, right? So there's nothing new that I have said. We have already discussed this, but I just wanted to quickly refresh it because it's relevant for the discussion. So now if the power of deep neural networks comes from such non-linearities, where do the non-linearities come from? The non-linearities essentially come from the activation function, and hence we need to discuss about these activation functions, right? What do these bring, and are there better activation functions possible is any nonlinear function okay, or you want certain better and better properties should be satisfied by these nonlinear functions. So that's what we are going to focus on today, right? So that's the reason why a discussion on activation functions is important, right? Now we'll look at some of the popular activation functions. Quite a bit of this material, at least the initial part, is taken from the lecture like a few years back, lecture slides from Andre Karpathy's course. I'm not sure if those videos are still available, but they were available a few years back, and I had taken material from there. So let's start with the sigmoid function. So sigmoid is given by this: sigma of x is equal to 1 over 1 plus e raised to minus x, and this is what it looks like. It is between 0 and 1. So whatever input you pass it, in our case, the input that we passed to the sigmoid function is sum a, which in turn is some linear transformation of the previous layer, right? We pass some ai, and it is some linear transformation of the previous layer, right? That's what our input is going to be, and whatever is the input, that applies element wise on this vector a, and it just squeezes it or compresses it between 0 to 1, right? So we already have seen this in the past. So now, since we are always interested in gradients, right? Because as I said, that training deep neural networks is largely about computing gradients, and then based on the gradients, either the training would go fast, slow, and so on, right? So let's see what is the gradient of the sigmoid function, right? And this again we have computed. If you have not, you can just take this as an exercise and try to find the gradient of, in fact we have, but you can just revisit it and try to compute the gradient of this function, and you will end up with this formula, right, which is sigma x into 1 minus sigma x, right? And now let's focus on this formula. So what could happen if we use sigmoid in a deep neural network, given that the gradient of the sigmoid is given by this formula, right? In particular, note that at the extremes, when the sigmoid neuron saturates, what do I mean by saturate? It takes its maximum value, which is 1, or if it takes its minimum value, which is 0, right, or close to 0, in those cases the gradient vanishes, right? So if I put sigma x equal to 1, then I'll get 1 into 1 minus 1, so the gradient will vanish, that is in this region. Or if I put sigma x equal to 0, which is corresponding to this region, then again 0 into anything is 0, right? So the gradient actually vanishes, and we know that if the gradient vanishes or if it's very small, right? So in these regions, starting from here, the gradient is very small, and that is a problem in gradient based learning methods, because the updates will not be high, right? So that's where this discussion is headed. So let's try to go there now, okay? So this is a deep neural network, and if I've used sigmoid nonlinearity, then in some point in this chain rule, right? Suppose I am trying to find the derivative of this weight with respect to the loss function. At some point, I am going to encounter this in the chain rule. I will encounter derivative of h3 with respect to a3, and you can convince yourself, right? I mean, any even if w1 or w2 or w3, if I am trying to find the derivative of this with respect to the loss function, then this guy is sitting in the path, so you will encounter that, and that is nothing but the sigmoid of the derivative of the sigmoid function with respect to a3, and that is given by this formula, right? So that's something that we will always encounter whenever we are doing back propagation with and using any gradient based method. So now what is the consequence of this, right? So as I said, there is this concept of saturated neuron. So a neuron is said to be saturated if it is at its peak or lowest value, right? Minimum or maximum value. In the case of sigmoid neurons, it's 0 or 1. So whenever it is saturated, the gradient is going to be 0, right? And if it is 0, then your training will not progress, because once the neuron is saturated, your gradients are 0. Now the weights are not getting updated, and then it's likely that because of these weights, right, especially if the weights are high. So let's see, why would the neurons get saturated, right? So let's try to understand that. Why is it that it would get saturated, right? It's not given, right, because the function can take values between 0 to 1. So why is it that it would suddenly become 1 or suddenly become 0, right? So let's try to answer that. So this, if I were to consider any such neuron in the network, right? So suppose this is one of the neurons. This is not the output neuron, but say some neuron in the network, and this is what the output of this neuron would be, right? It would be the sigmoid of the linear combination of the inputs connected to it, right? So this is what the output would be. Now, suppose I have initialized the weights to a very high value, right? Suppose my weights are, say, suppose 100, 200 and so on, and now my inputs are all standardized, right? We anyway standardize the inputs. That means we divide by the, subtract the mean and then divide by the variance. So all our inputs are between 0 to 1. So the inputs are typically standardized. That's anyways recommended for using gradient based methods. So the inputs will not cause a problem. They will be anyway small between 0 to 1. But if the weights are initialized to high value, then this sub wi sigma I is, wi xi is going to be high. And remember, see in the plot, even for values like 2.5, the sigmoid neuron has already saturated, right? On the x-axis you have 2.5 and on the y-axis you have almost 1, right? So if your weights are initialized even reasonably high, then your neurons, the sigma, the quantity passed through the sigmoid neuron is going to be a high quantity, and then for that the sigma is going to be close to 1, right? Similarly, if the weights are initialized to high negative value, the same would happen. You would have a high negative value and the neuron would saturate to 0. Now, of course, you could argue that why would the weights be high, right? I would maybe initialize them to low values. But now, if there are like 1000 neurons in one layer, right, then this is a sum of 1000 terms. And even with very small weights, a sum of 1000 terms reaching a value of 2 or 3 is not really surprising. Right? So you have to very carefully initialize the weights, and that's why this part would be connected to the second part of this lecture, where we'll talk about weight initialization methods, and we'll try to see how to initialize the weights correctly so that we don't end up with saturated neurons, right? So the main point here is that neurons can saturate, and if they saturate, then the training kind of becomes problematic because the gradients are not flowing through, right? And if the neuron is saturating with a value 1, that means actually these weights were like strongly participating in the output, right? And hence they would have had some impact on the loss function, but that signal will not flow back to these weights because the derivatives have died, right? So that's a serious problem. So this could lead to challenges during training. Since this is not good, the next problem is that sigmoids are not zero centered. That's again obvious from the plot because the plot is from 0 to 1. Zero centered would be something like, say, for example, -1 to 1. So there is a 0 in between. So it's equally distributed around 0. Whereas this itself starts from 0 and goes to 1. So the center is around 0.5, right? So what if it's not zero centered, right? What could the problem be, right? So now let's try to again see that through an example. Suppose I have this output layer, and before that I have this one sigmoid neuron, right? And it is connected to two inputs, H21 and H22. So I'll have the A3 would be this, and then I'll passing it through the sigmoid neuron, right? Now again, if I were to update the weights W1 or W2, let's see what chain rule I will use there. So this is what my derivative would be, right? So it would be derivative of the loss function, which is sitting here with respect to y, right? Then the derivative of y with respect to h3, so the output is h3. Then the derivative of h3 with respect to a3, right? And then the and then the derivative of a3 with respect to w1, which I have already written as h21. So this is what a3 is. If I take the derivative of this with respect to w1, this quantity disappears because it's a constant, and the derivative of w1 h21 is just h21. Similarly, the derivative of w2, or rather of the loss function with respect to w2 would have an h22 here, right? Again, because derivative of a3 with respect to w2, this quantity would disappear and you will get an h22, right? So this is fine. This formula you understand. Now what's with the color coding, right? What's the red part and what's the blue part? So the red part is common for both the derivatives, right? So this part is actually the same in both the derivatives, okay? And this part is changing, okay? This is h21 and h22. Now what is h21? h21 is the output of the previous sigmoid neuron, right? So I know that this is going to be positive, right? Both the blue quantities I know are going to be positive, right? Now if both the blue quantities are going to be positive, then the sign of these two gradients is decided by the red quantity, right? And the red quantity is the same for both the gradients. So now both the partial derivatives. So now either the red quantity is negative, in which case both these derivatives are negative, or the red quantity is positive, in which case again both these derivatives are positive, right. So, I cannot have a situation where I have my gradient vector which contains all these derivatives, and either it will be all positives or it will be all negatives, right. And this would be true even if I had like n neurons here, the same argument I could have extended to it. So, if I had computed those n partial derivatives, I would have had this red term common, and then this blue term. The blue term is always positive because it's the output of a sigmoid neuron, so it has no say on the sign, and then the sign is then determined by, or rather, I mean, it contributes equally, I mean, whatever it is, all of it is positive. The sign will just depend on the red part, and the red part is same for all these guys. So, if the red part is negative, all of them would be negative, it's positive, all of them would be positive, right. So, a gradient vector is either consisting all positive values or all negative values, right. So, that's what is happening. And why am I discussing this in the case of sigmoid neuron? Because this happened because you had used sigmoid neurons, hence the blue parts were always positive, right. If you had used some other neuron which had a range between -1 to 1, then it would have been possible some of these blues were positive, some of these blues were negative, and then accordingly the vectors, the elements of the vector, some of them would be positive, some of them would be negative. But because you are using a sigmoid neuron, all the blues are positive, and hence all the elements of the gradient vector would have the same sign. Now, what is the problem with that? That is, I've just told you what is happening, but we don't know what the problem with that is, right. So, this is just in words whatever I explained. So, let's see what the problem is, right. So, this is the say derivative of the partial derivative with respect to W1, partial derivative with respect to W2. So, now if I consider the plane, right, which has all possible values of partial derivative of W1 and W2. So, now which are the quadrants which are possible? Either the quadrant where both the values are positive, or the quadrant where both the values are negative, right. So, you can never have a vector in this direction. Your gradient vector cannot be in this direction, nor can be it in any of these directions. It can only be in these directions or these directions, right. That is what this previous explanation is telling you. So, you can already see that when you are doing gradient descent, you are moving in directions. Now, half the directions have been thrown away because of using the sigmoid neuron. These directions are not possible at all, right. So, you can only move in certain directions, and that already looks like a problem. And here's a toy example to show that it is indeed a problem, right. So, suppose you have initialized, suppose this arrow here, this is the optimal value of W, right. This is where you want to go, and suppose this is where you had initialized your weight, right. So, now I would want to have a possible movement like this, right, and reach the optimum, but this movement is not possible because it has one value positive, one value negative, and we know that that is not possible. We already saw that all these kind of movements are not possible, right. So, this is not going to be possible. So, now how will I have to reach the optimum? I will have to just take the movements which are allowed. So, I will have to perhaps take this movement. This is okay, wait, this is allowed, yeah, this is allowed, right. So, this is where like one is 0 and the other is negative, so that is allowed, this and so on, right. So, I will have to move like this in a zigzag pattern to kind of reach the optimum, right. So, I will take more steps to converge, and keeping this toy example aside, right, the simple thing is this, right. So, I am asking you to go from place A to place B, but I am saying that hey, certain types of turns are not allowed. If you are not allowed to take certain types of turns and you are restricted only to some types of turns, then you are going to take more time, right. So, that is the main idea, and that is happening because sigmoids are not zero centered, hence you get all values as positive, hence this negative positive combination is not possible in the directions that you choose to move in, right. And lastly, of course, sigmoids are computationally expensive because you have the exponent to compute. Of course, there are faster ways of computing it, but still it is a computation that you need to do, right. So, that is the other reason. So, that is all about the sigmoid neurons and why they are not the most convenient activation function. So, then because of these limitations, right. So, at some point, so now because of these limitations, the tanh function is popular because one of the things that you immediately see is that it's zero centered, right. And then whatever explanation I gave at the end, that is kind of taken care of. Of course, Tanh is not a new activation function, it has been used since 1990s, but we are just going over all the activation functions. So sigmoid is the default that we start explanations with, but now have shown you certain problems with it, and then Tanh overcomes some of those problems. It is zero centered, but let's see what is the derivative of this, right? So derivative of this is 1 minus Tanh square x, and again at saturation the gradients will vanish, right? And that you don't need to look at the formula. It's the same problem as the graph itself shows you, that if the function value lies here, then the derivative is very small or zero. Same thing here, right? And if you look at the formula, so when Tanh square is 1, your derivative would be 0, right? Or when it would be minus 1, right? So whenever it is plus or minus 1, your derivative is going to be 0, right? So that's again clear. So the problem of the saturating neuron and hence the gradient vanishing still exists. The problem of limited directions to move in has been overcome, and also the problem of computational expensive still remains, right? Because still it has the E component in it, right? So Tanh, the formula contains the E part of it, right? So yeah. Okay. So the next next activation function that we look at is the rectified linear unit, and this is one of the most popular activation functions. As we'll see at the end of the discussion, we'll show you what are the popular activation functions, and this is proposed almost a decade back in the context of convolutional neural networks, and it's still one of the de facto activation functions to be used across a wide variety of networks, right? The first question that I have, this is what the Relu function looks like, right? So it is simply max of 0 comma x, right? So what does that mean? That again in the context of a deep neural network, so say this is one of the neurons, right? So this is suppose my H1, this is say x. Now I have computed the A's, right? So this guy here, let me call it say A12, right? That is going to be again summation Wi xi, that we know, right? Now that is, this A12 is going to be the input to the Relu function, that is the non-linearity sitting here, and it will simply look at whether A12 is greater than 0. If so, it will just return A12, otherwise it will return 0, right? So if you have any negative value being passed to it, it clamps it to 0, and if it's a positive value, it just let it be as it is, right? So let's see what are the implications of that, right? So the first question is that, is this really a non-linear function? So indeed it is a non-linear function. The max function, the way it is shown here, is a non-linear function. A linear function would just behave linearly on both sides, but this is on the negative side, you have clamped it. And in fact you can show that if we combine two Relu units, right? So these are two Relu units that I have combined, right? So this is a Relu function and this is another Relu function, and I have just taken the difference between these two, right? So you could think of it in terms of neurons. I had two neurons, both of these were Relu neurons, right? And then I am subtracting one from the other and I am getting some output, and that output looks almost like the sigmoid function, right? It looks like a linear approximation of the sigmoid function. So it is indeed a non-linear function, right? It's as close to almost like the step function that you have, and if you adjust these parameters a bit more, you will get even better kind of a step function and so on, right? So indeed Relu is a non-linear function. Some of you have not seen it before, might just look at the line and think that it's a linear function, but it is not. Okay, this specific function that I've drawn is called Relu 6 because 6 denotes the maximum value of the Relu that you have here. Okay. Okay. So what are the advantages of Relu? So it does not saturate in the positive region, right? What do I mean by that? So as long as your A3, right, or A was positive, the output would remain positive and it will not saturate, right? There is no saturation here. There is no clamping on this side as opposed to what you had in the sigmoid or any of the sigmoid shaped functions, right? So that is what I mean here. But in the negative region, it can still saturate, right? So if your contribution is negative, right? If the A is negative, then it will be clamped to 0, and of course the derivative would again then be 0, right? So it does saturate in the negative region, so roughly half the problem solved. But computationally it's of course very efficient, right? There is no exponent here, you just look at the value and the simple implementation is if greater than 0, pass it, right? So it's a very simple function to compute, and in practice, at least that's what this paper, and as I said, it's a decade-old paper, had shown that it converges much faster than Sigmoid and Tanh, and this was in the context of deep convolutional neural networks then, but thereafter it has been used in all sorts of networks, as I said, right? Feed-forward networks, recurrent networks, transformers also, right? Although now in transformers there's the Relu activation function, which is perhaps the default, but yeah, this has been used in multiple contexts. Right? So now, although this all sounds good, right? So what all sounds good? One is it does not saturate, at least half the times it does not saturate, as opposed to Sigmoid and Tanh, which have 2 saturation regions. It's computationally efficient. So these 2 things are taken care of, but still there is some challenges here, right? And we'll see what those are. So if you look at the derivative of Relu, then it is going to be 0 if x is less than 0, and it's going to be 1 if x is greater than 0, right? That simply follows from the fact that Relu is equal to 0 or x. So when it's x, the derivative of this with respect to x is just going to be 1, right? So this is what the derivative looks like. And now if this is what the derivative looks like, let's see what's the implication that we have, right? So I've given you some toy example here, a toy network. Now at some point, suppose there's a large gradient which flows through the network, right? There's a large gradient which flows, and it makes B's value very negative, right? Suppose B takes on a large negative value. Okay, that is what happens, and this is not like cooked up. This is conceivable that this could happen. You have some training example which causes B to update, and then B becomes a very large negative value, right? Now, if that happens, what would the consequence of it be? So now your A1, right, which is the input to the Relu function, right? The Relu function is sitting here, is just W1x1 plus W2x2 plus B. Now, if B is very negative, irrespective of what W1x1 and W2x2 are, right? This B, a very large negative quantity, would get added, so this is going to be 0. So if this is going to be 0, then the derivative is going to be 0. So if the derivative is 0, again you have this problem that when you are trying to update W1, at some point in the chain you have this derivative of H1 with respect to A1, and that derivative is going to be 0, right? Which means the derivative of the loss function with respect to W1, W2 is going to be 0, right? Now if, and also with respect to B is going to be 0. So now if that happens, the neuron of course outputted zeros, the neuron's output was 0, which means it was a dead neuron, which is fine. If it's dead for this training example, I can live with it, right? But now it's not got updated, neither has B gotten updated, right? And now from here on, what will happen is that the neuron will remain dead for the rest of the training. It will never become alive again, right? So why is that the case? So this is all just the explanation that I gave in, just I was speaking through it. This is all on the slides also. And this is the main point that I'm talking about now, right? That the neuron will stay dead forever, right? So why would that happen? Yeah. So weights are never getting updated, right? So once it became dead, W1, W2 and B, all 3 will not get updated, right? So B still remains this large negative value. Now the next input comes in. Again the same will happen. The B is this large negative value. So this sum W1x1 plus W2x2 plus B would again be less than 0. Again the neuron is dead, and then again the gradient does not flow through. Again W1, W2, B don't get updated. Again the next input comes in, it's the same story, right? So once it becomes dead, it stays dead forever, right? And in practice people have observed that as high as greater than 50% of the Relu units can die if the learning rate is set too high, right? Why is this related to the learning rate? If the learning rate is very high, then this problem of a large gradient flowing to B and then getting multiplied by a reasonable learning rate can cause B to be very negative, right? So that's why the learning rate has to be carefully carefully set. And also when you are using Relu, it is advised to initialize bias to a positive value, right? And in context of deep learning, this is a fairly large positive value, 0.01, because you have many elements contributing to the sum, so one of them is 0.01, right? So you should set it properly, otherwise many of your neurons would die, or you could use some of the other variants of Relu that we will see soon. So this is one variant, which is the leaky Relu, right? And as the name suggests, it's allowed some leakage on the negative side. So earlier, whenever you had a negative value, you were kind of making it 0. Now you make it small. You multiply by a very small constant, so it becomes small, right? So it's close to 0, but it does not die completely. So it allows some gradients to flow even when your x is negative, right? So it takes care of neurons not saturating, and it will not die because it will ensure that some gradient always flows through, and it remains computationally efficient, right? Just making it 0.1x does not make it any more expensive than the Relu function, right? Maybe slightly more expensive, right? And also it gives you these close to 0 centered outputs, because now you have outputs which are negative also, and you have outputs which are positive also. So this problem of gradients only being in one direction is also taken care of, right? So multiple advantages of leaky Relu. And then there are a few such other variants, right? So one of them is parametric Relu. So then the question is, right, that why set this to 0.1x, right? So let it be some alpha, and this alpha could also be learned, and it will also get updated during backpropagation, right? So one simple way of thinking is that you set alpha equal to 0.1 to begin with, right? And then just as all the weights are getting updated, compute this derivative of the loss function with respect to alpha also, and then update alpha also as alpha minus eta times this gradient, or whatever gradient descent update rule you are using, right? So this is kind of again makes it more careful that why have you selected a certain slope here, maybe that slope needs to be adjusted as the training is going, right? So it gives you more flexibility, and again takes care of all the problems that you had with Relu of neurons dying and it not being 0 centered, right? While these variants have been proposed, they are not like so popular. I think Relu, the default version, is still the most popular among these variants. Yeah. And one more variant of Relu is the exponential linear unit, right? So so far everything was linear on both sides, right? It was like this, but now on the whenever the input is less than 0, we are making it exponentially decay. So there's still some gradient flowing on the negative side also. It has all the benefits of Relu because largely it has linear on the positive side, and it's also now again close to 0 centered, right? And some gradient always flows through, but it again becomes exponentially it becomes expensive, right? Because you have to compute this exponent, right? So now all of these, they were proposed in certain contexts, and in those contexts they were like found to be better than Relu. Also some of them theoretically showed that why they are better than Relu, but at least in practice many of these are not very popular, right? You just use the default Relu and largely that works, or you use some of the more recent ones, which is Gelu and Swish, right? So they are more popular now, right? So that ends the discussion on three of the most popular or three of the initial activation functions which were there around 2012-2014, which is the logistic activation function, then the Tanh, and then the Relu, right? So I'll end this video here, and when we come back we'll discuss a few more later activation functions that came.